Therefore, the polynomial function g of x equals 2x cubed plus 5x squared minus 28x minus 15, part A, determine the maximum number of real zeros that the function may have. The degree of g of x is 3. Therefore, the maximum number of real zeros is 3. Part B, list the potential rational zeros. The constant term of our polynomial function g of x, a sub 0, was equal to negative 15. Let's let p represent all of the integer factors of negative 15. Integer factors of negative 15 include plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. The leading coefficient of g of x was equal to positive 2. Let's let q represent all of the integer factors of positive 2. They include plus or minus 1 and plus or minus 2. We will now list all possible ratios of p over q. From small to large, and also in lowest terms, our p over q list include plus or minus 1/2, plus or minus 1, plus or minus 3/2, plus or minus 5/2, plus or minus 3, plus or minus 5, plus or minus 15/2, and plus or minus 15. If function g has a rational zero, it must be one of the 16 possibilities listed. Part C. Determine the real zeros of function g. Factor g over the real numbers. We can find the rational zeros of function g by using the fact that if r is a zero of g, then g of r must equal 0. That is, we will evaluate the function for different values from our p over q list, hoping to get g of that value to equal 0. From our p over q list, let's say that we choose positive 3. Evaluating function g at 3, we would get 2 times 3 cubed plus 5 times 3 squared minus 28 times 3 minus 15. g of 3 would then be equal to 54 plus 45 minus 84 minus 15, which equals 0. Therefore, we know that 3 is a zero of g of x. Since 3 is a zero of the function, then that implies that the quantity x minus 3 must be a factor of g of x. So with that fact, we will use long division to now find the other factor or factors of g of x. When we divide 2x cubed plus 5x squared minus 28x minus 15 by x minus 3 using long division, we can see that the quotient is 2x squared plus 11x plus 5, and we do get a remainder of 0. Thus, not only is the quantity x minus 3 a factor of function g, but the quotient 2x squared plus 11x plus 5 is also a factor of g. So now we know, by using long division, we know that g of x, which was equal to 2x cubed plus 5x squared minus 28x minus 15, we now know we can rewrite g of x as the quantity x minus 3 times the quantity 2x squared plus 11x plus 5. Our quadratic factor, 2x squared plus 11x plus 5, can be factored further. Our quadratic factor can be factored as the quantity 2x plus 1 times the quantity x plus 5. Thus, the complete linear factorization of g of x is equal to the quantity x minus 3 times the quantity 2x plus 1 times the quantity x plus 5. Earlier, we already concluded that 3 was a zero of g of x. To find the other zeros, we will now set the other two linear factors, 2x plus 1 and the factor x plus 5, we will now set those equal to 0 and solve. Setting the factor 2x plus 1 equal to 0, we will get x is equal to negative 1/2. Setting the factor x plus 5 equal to 0, we will get x equals negative 5. Therefore, the zeros of function g are negative 5, negative 1/2, and positive 3. Find the x and y intercepts of the graph of g. Let's start with finding the x-intercepts. Earlier we concluded that the zeros of function g were negative 5, negative 1/2, and positive 3. X-intercepts of a graph are the same as the zeros of a function. Thus, our x-intercepts will occur at negative 5, negative 1/2, and positive 3. To find the y-intercept of function g, we will simply evaluate g of 0. G of 0 will equal 2 times 0 cubed plus 5 times 0 squared minus 28 times 0 minus 15. This is equal to negative 15. Therefore, the y-intercept of the graph of g is at negative 15. Part E. Determine whether the graph crosses or touches the x-axis at each x-intercept. Whether the graph crosses or touches at an x-intercept is determined by the multiplicity. So looking at the factored form of our function g of x, we can see that each factor only occurs once. Thus, the multiplicity of each 0 is 1. For odd multiplicity, the graph will cross the x-axis at the 0. Thus, the graph crosses the x-axis at each of the 3 x-intercepts. Thus, the graph of g will cross the x-axis at x equals 3, will cross at x equals negative 1/2, and will also cross the x-axis at x equals negative 5. Part F. Find the power function that the graph of g resembles for large values of the absolute value of x. The power function that the graph of g resembles is given by the term with the highest power of x. Going back and looking at our function g of x, we can see that the highest power of x is 3. Our leading term is 2x cubed. Thus, the graph of g will resemble the power function y equals 2x cubed. Part G. Put all the information together to obtain the graph of g. We begin with a blank xy grid. The x-axis spans from negative 5 to positive 5 in increments of 1, and the y-axis spans from negative 50 to positive 60 in increments of 10. To begin, let's plot our x-intercepts and our y-intercept. We plot the points negative 5, 0, negative 1/2, 0, and 3, 0. Those are the x-intercepts. The y-intercept we found to be at the point 0, negative 15. We plot 2 more additional points to get an idea of where our graph will go. So let's choose to let x equal negative 2. G of negative 2 is equal to positive 45. And also, g of 1 is equal to negative 36. We know that the graph will behave like y equals 2x cubed. Therefore, our graph will enter in quadrant 3, cross the x-axis at negative 5, and then turn in quadrant 2 and go through the point negative 2, 45, cross through the x-axis again at negative 1/2, pass through the y-intercept at 0, negative 15, and also pass through the point 1, negative 36, where the graph will then turn again and turn again in quadrant 4, and then come up and cross the x-axis again at x equals positive 3, and continue upward and exit in quadrant 1.